In this video, I want to look at what it means to integrate with respect to y, because some regions in the xy plane are more naturally set up as what I think of as sideways or right-left regions. And that means we need to be able to interpret what it means to integrate with respect to y. So I'm going to actually draw a standard kind of xy plane, but this time I'm going to draw a curve that looks like this. Now, this is clearly not a function of x because it violates the vertical line test, but it does turn out to be a function of y. In other words, I can write x is equal to some function of y here. And if I draw a line here that is at A, and I draw another line here that is y is at B, so these are horizontal lines, so they are y is A, y is B. If I shade in this area here, it turns out that because that area is in the y sense on the positive side of the y axis, that area turns out to be the integral from a to b of f of y dy. And one way that we can see this is if we thought about drawing rectangles, our rectangles would look like this. Actually, let me draw this color shows up a little bit better. Our rectangles would look like this. And I would be picking samples of rectangles like this, but the width of the rectangles would be positive because the width of the rectangle would be f of y minus 0. So that would be my width of a rectangle, and because f of y is bigger than 0, we would be getting positive rectangles. So that would be how I would look at this kind of a region. Now, I want to kind of look at what happens if I'm integrating with respect to y and the function is negative. So I'm going to just draw another picture here. So suppose my region looks like this. So this is now y, dot y, this is going to be x. So x is equal to f of y is over here. And this is the y-axis, and this is the x-axis. And here is A, and here is B. And again, these are y lines because they're horizontal lines. And if I color in this area here, what I want to notice is that it is to the left of the y-axis, and just like being below the x-axis, it turns out that if I integrate from a to b of f of y dy here, I'm going to get minus the yellow area. And the reason why is that, again, if I start thinking about trying to chop this up into rectangles, using our Riemann sum definition, the widths of the rectangles here are equal to f of y, and f of y is less than 0 because the function is to the left of the y-axis, and over here x values are less than 0. And so the area winds up being a negative area. Well, what that actually means is that in the overall idea, if I'm integrating with respect to y of a function f of y dy, this turns out to be a signed area, just like a definite integral with respect to x does, but the interpretation of the signed area is slightly different. So I'm going to draw one more picture here. I'm going to have a picture that is doing something like this. So this is now my x is equal to f of y. And I'm going to have my A, B, let's make the A here. So this is y is equal to a, and this is y is equal to b. And what I want to notice is that I've got two chunks of area. I've got an area here that is to the left of the y-axis, and I have an area here that is to the right of the y-axis. And let me extend that y-axis up where I can label it. And I'm going to call this chunk of area, that chunk of area is going to be labeled A1, and this chunk of area is going to be labeled A2. Well, the signed area is going to treat A1 as negative because the x values are negative. In other words, the width of the rectangle is negative. And it's going to be treating A2 as a positive area. And let me get consistent on my colors. And so this integral would be minus a1 plus a2. In other words, the more general case is that a definite integral from a to b of f of y dy is going to be the area to the right of the y-axis minus the area to the left of the y-axis. And what this means is that we can then generalize area between two curves in the same way that we did on the x direction. We'll look at that in the next video.